Hello everyone. Today we are going to discuss in the last point of the topic, that is the theories of trans effect and their applications. In this today's lecture we are going to concern on the theories of trans effect. Okay, there are two theories. First is known as electrostatic polarization theory, and second is known as a pi bonding theory. Now we have to emphasize on this theory in the concept of a Fajon's rule. Fajon's rule of polarizability. Polarizability. It is what, in short, I am telling you. That is when an ligand develops its polarities around delta positive, delta negative. Suppose here it induced its magnetic dipole moment. Due to this inducement of this magnetic dipole moment, it induces its central metal ion with a charges of delta positive and delta negative. Thus, the electrons, whatever may be the electrons here of this induced element, gets attracted, and in the positive point of this central metal ion there will be attraction of these two elements, that is of central metal ion and the ligand, and thus the bond between this M and X becomes the strong. And the same time, whatever may be the another bond with metal ion with the leaving group, that is called as L, this bond gets weakened, because as there is a attraction between delta positive charge, delta negative charge and delta positive charge here, what happens here? Attraction between the two kinds of the metal ion and the ligand. While here central metal induces the dipole in which polarity? Delta negative, and already the ligand which is to be leave, that is having the charge as negative. The negative means repulsion. Already we know that this. By using this concept, we have to explain the electrostatic polarization theory. And the sigma and the another theory is known as a pi bonding theory. By using the d pi, p pi or d pi, p pi back bonding of this platinum with a ligands, how the bond is weakened between platinum and the leaving group of a ligand. This can be explained in the pi bonding theory. In short, we can say that here, that is, in this electrostatic polarization theory, what happens? That is when ground state of a reactant, it gets increased. What happens? That is the gap between the reactant and the activation energy, it gets lowered. And when the activation energy gets lowered, what happens here? Also gap between the activation energy and the reactant, it gets lowered in order to weakening of the bond between the leaving group and the central metal ion here. Okay, so let us discuss this theory, that is electrostatic polarization theory. First of all, I will draw some diagrams. Okay, see here the diagrammatic representation, that is M central metal ion here. Okay, on second L. Okay, here having the delta minus, delta plus, delta minus, delta plus here. Here also delta plus, delta minus here. Okay, here also in which, that is the X. Okay, here delta plus, delta minus here. Here also a X. Okay, here delta minus, delta plus. Here also a X. Here delta minus, delta plus. Okay, this is MX4. Okay, A diagram. Now in the second diagram, what happens here? See the second diagram, that is here. Suppose the ligands, this is all the same ligands, that is M here, all the ligands are here, that is here the L3, L1, L2, L3, and here the X. Now in this here, what happens here? That is, here it includes develops the polarities as delta plus delta negative. Here central metal ions gets here, that is the delta plus delta negative here, and here also what happens here, that is here delta negative one. Okay, now here also these are the ligands L1 and here L2, delta minus delta plus here, delta minus delta plus here. Okay, now the bond between these bonds is known as that is a shortening and strong bond, and this bond is again weakening and lengthening of bond. And thus we get here as, what we get as here, the distance that is equal to here, this is L3, this is M, this is X, okay, this is also L1, here also L1, and here L2, here these are the strong bonds, okay, strong and short bond, strong and short bond here, and this bond is a weak and long bond and elongated bond here. Now what's going to here? See here, this is the diagrammatic representation of electrostatic polarization theory. Okay, what happens? See the diagrams. This is a diagram, this is a B diagram, and this is a last C diagram. Okay, now when all the ligands, when coordinated to central metal ions of same kind, they cancel their dipoles, and thus the net dipole moment is equal to what? That is the 0. That is all the ligands of their dipole moments getting cancelled to each other. Thus there is a null charge. Now suppose that this central metal ion of a square parallel complex of 3 ligands of one category and only one ligand is of second category. These ligands are L1, L2 and L3. Okay, these are of same kinds. Therefore these two ligands, they can cancel their dipole moments by developing its polarity. Now according to Fragments polarization theory, here what happens? First, suppose that the L3 ligand is more polarizable than which? Than the X ligand. First of all, we have to suppose that is the ligand L3 is more polarizable than X. Now here what happens here? See here the diagram. When L3 is more polarizable than X, at that time what happens? It induces the dipole. It induces the dipole polarities as delta X and delta Y, as delta X, delta positive and delta negative within itself. That is of this delta positive and delta negative. Then it induces the dipole in the central metal ion by accepting the electrons of the central metal ion to itself. That is, in this ligand itself, it has some number of ligands over some number of electrons, and it can hold by its nucleus. Okay, thus it is a more polarizable. Thus it is a polarizable one here by differentiating the polarities as a delta positive and delta negative. When this ligand, that is L3 ligand, induces the dipole in the central metal ion, that central metal ion has a polarities are delta plus and delta minus. Okay, now already on that side here L3 ligand has a polarity delta negative and here delta positive. Due to the opposite polarities, there is attraction of the electrons. That is, some of the electrons of central metal ions gets absorbed by this electron cloud of this L3 ligand. Thus, this covalent bond, there is formation of a covalent sigma bond, becomes a stronger one. But at the same time, what happens here? Whatever may be the polarity in the right side of this central metal ion is what? That is the delta negative. And as the X is a what? That is a leaving group here a leaving ligand. Here it has also a polarity that is equal to delta negative. Therefore, both the polarities can repel with each other according to physics law here. Okay, that is attraction, repulsion. Attraction, here positive and negative pole, here attraction, and positive repulsion, negative also a repulsion one. Then both the charges are same, therefore there is repulsion. They are apart from each other, so as to here this bond distance gets lengthening, and as the bond distance gets lengthening, the bond becomes a central metal ion, and the X gets to be at high distance. That is this bond length. This is the bond length should be of a higher distance as compared to this bond length. That is, this bond length and this bond length same is here. Okay. Therefore, this bond length gets shorter and this bond length gets elongated. Okay. Therefore, there is breaking of the bonds. What? Due to what reason? Because as the ligand L3 is more polarizable, it can direct its trans effect, that is delta negative, with a side opposite to the centrum, opposite to this L3 ligand. Thus, by replacing of this X ligand by an entering ligand, thus the bond between the central metal ion and the leaving ligand gets weakened, and thus it can be break here. Okay. Therefore, by using this pi electrostatic polarization theory, we can explain why there is weakening of the bond between central metal ion and the X, that is a leaving group here. Okay. Thus, what we have seen here, that is out of the three ligands, that is L1, L2 and L3, this distance, okay, this distance gets as a shorter distance, but this bond becomes a strong bond, that is sigma bond. And as this distance gets elongated, that is the bond length is elongated, the weakening of the bond between this central metal ion and the X gets weakened, and thus the bond between the central metal ion and the X gets breaks away. Okay. Now, which of the points we have to discuss here again? Again, I am reminding in short. First, when the ligand L3 is more polarizable than X, first it induces the dipole with polarities delta plus and delta minus. Then it is also dipole, induces the central metal ion as delta plus and delta negative, but in the direction of that is L of delta plus, L of delta negative comes with a central metal of a delta plus. There is a whatever be the bond between this ligand and the metal ion, it becomes a strong one, and this bond is known as a sigma bond. At the same time, what happens? As central metal acquires the polarity delta negative, and the other ligand, say X, that is the leaving group, acquires polarity negative, delta negative, both the polarities are of same time. Therefore, there is a weakening of the bond between M and X here. Okay. Thus, we have here explained that why the bond between this M and X gets broken. Why? Because here, as the ground state energy of the reactant, suppose this is a reactant. Okay. This is the original graph here. Okay. From our energy versus reaction progress. When this energy, this side of this energy of a reactants, it gets increased. That is from here, what is the electron gap here? It is a very small electron, very small gap. That is the gap between reactant to activation energy. It is called as a energy of activation. It is very small, which is responsible for the weakening of the central metal ion and the leaving group bond here. In this way, we have explained here polarization theory. Now, this theory has some advantages. Okay. What are its advantages? There are 3 advantages. That is, trans effect is explained by using only platinum square complexes of D8 configuration. Also platinum, palladium, Au and nickel +2 oxidation state. Second is what? That is by using this only here, the trans elements are here. Now the second advantage is that here, that is it follows from the structures, that is the from complexes here, complexes. For example, the distances, how the bond lengths are elongated, bond lengths are get shortened here. For example, C2H4, here platinum, okay, Cl, here also a Cl. This bond distance is a 2.32, okay, and this bond distance is a 2.42. This is also a 2.32. Again, C2H4, okay, platinum, Br, okay, or instead of X, we have to take the M here, that is Br, here 2.42 and here 2.50 angstrom. Okay, this is of Br. Okay, by using this example, one can see that how the bond length is elongated, and that's why the bond between the central metal and the leaving group gets weakened. As the bond length is shorter, the bond becomes strong. As the bond length is elongated, okay, here the bond is weakens. Also here, this is distance is equal to 2.32 angstrom, platinum and chlorine. But here in this platinum and this of a chlorine, this is a leaving group here, therefore its distance gets increased, that is equal to 2.42. Also here MBr bond gets weakened, its distance equal to 2.5 angstrom here, and that of this M and Br, that is distance is about 2.42. Okay, the next point is that here, that is transdirecting ligands. Okay, transdirecting ligands are either polarizable. First, transdirecting ligands are either polarizable or having capacity to form the pi bond. To form pi bond here. Okay. For example, the ligands like CO and here also a Cn minus. Okay. Now, this theory has some limitations also. These are the advantages, limitations. This theory only explains how the weakening of bond between M and X here. That is the leaving bond. And due to that, any one of these other criteria cannot be explained here. And the second limitation is that this theory is not applicable in case of which, that is CO, Cn minus, okay, etc. ligands. As the theory is not applicable for CO, Cn minus ligands, that's why the second theory is put forwards. That is known as a pi bonding theory, which explains the trans effect in case of the ligands like a CO and Cn here. Okay. Now, how the platinum can use the back bonding here. First of all, this point is remain one. Here, this is the platinum. These are the square planar complexes here. This is X, this is X, okay. Sorry. This is A, okay, and this is also A. Now, in the platinum square planar complexes, this is called as a leaving group. These are the bonds are formed by the platinum and the ligands with a bonding between of a platinum that is equal to px and dx square minus y square. Okay, that is, these bonds are nothing but the strong bonds. Okay, now in case of this, also due to the platinum donates its electrons back to its ligands like A1, there is also a d pi bonding or d pi p pi bonding, back bonding is also a takes place. This criteria we have to explain in the next theory, is called as a pi electron theory. Okay, now how the bonding between this platinum, or how platinum uses its bonding between a other ligands along with this leaving ligand, this type of study we are going to see in the next lecture, that is in the pi bonding theory. In the next lecture we are going to see the next theory and its applications. Okay, thank you.